How is it that we find ourselves surrounded by such complexity, such elegance?
The genes of you and me, the genes of you and me, we're all made of DNA. We're all made of the same chemical DNA. We're all made of DNA.
Hi, you're listening to DNA Today, a podcast and radio show where we discover new advances in the world of genetics. From genetic technology like CRISPR to rare diseases to new research, we have you covered. For a decade, DNA Today has brought you the voices of leaders in genetics. I'm Keira Deneen. I'm a certified genetic counselor and your host. We're joined by two mitochondrial experts who are very active in the rare disease community. We're focusing our conversation on a condition called Leber Hereditary Optic Neuropathy, which is shortened to LHON. My first guest is Lissa Poincenot. She is a patient advocate with the United Mitochondrial Disease Foundation. Her son has been diagnosed with LHON. And we also have Devin Shuman, who is a genetic counselor at the Genetic Support Foundation, who has also her own nano-rare mitochondrial disorder called GUK1. And before we get into all kinds of mitochondrial information, I wanted to give a shout out to a previous episode 168, for more information about mitochondrial disorders, specifically primary mitochondrial myopathy. So thank you both so much for coming on the show.
Thanks for having us. This is fun.
Thank you.
So I wanted to start out by saying that mitochondria provide energy. I think that's a very good baseline to start out. And a lot of people will remember that it's the powerhouse of the cell. I know that's what I think about when I go back to like high school biology, AP Bio, all of that. But how does the mitochondria actually provide energy? Can we add on to this definition a little bit?
I mean, I think that's where we're all starting from, right? Like we're all starting from it's the powerhouse of the cell, or sometimes people have heard the battery metaphor. And that kind of can work well. You've got batteries, it gives your body energy. The way that it actually makes that energy, though, I think of it as a lot like hydropower. So we have these mitochondria complexes that water flows down through, or in this case, ions, and there's a protein gradient, fancy terms. Water is how I picture it. And at the very end of that chain, there's actually a little turbine that it turns, and that's what helps make ATP. So it's just like water power. At the end, there's that spinning wheel, and that's how we generate energy from it. Now, there's really complicated diagrams online, but that's how I store it in my head and try to explain it to patients, because I think it sticks a little bit better.
Yes, that's much more clear than a lot of the diagrams I studied in college and grad school and everything, where, I'm revisiting those before this interview and I'm like, wow, there's a lot of details there. So for people to understand, what are some general symptoms for people that have mitochondrial disorders? Because there are mitochondrial disorders. It's not just one.
Yep. So essentially, I think of mitochondrial disorders kind of like saying heart disease. We're talking about an organ, we're talking about a little organelle, but there's a whole bunch of different flavors of it. And so kind of the rule of thumb, which makes it a little bit of a pain in the butt for doctors sometimes, is any symptom anywhere really can pop up with this. Because if you think about it, everything in your body requires energy to function. So if your body's having trouble making energy, anything has that potential to fail or not work as well as it should. There are hallmarks. People will say if you have 3 symptoms or more, think mito, so 3 different organ systems. That's not a hard and fast rule. Some people say, well, it's based in fatigue or muscle weakness. Again, not a hard and fast rule. So it makes it really difficult because you can present as an infant, you can present as an adult, you can have one organ system involved, like just the eyes, you can have most of your organ systems involved. There are some that have nice, easy names like LHON, or another common one is called MELAS, where there's 1 or 2 main symptoms. But honestly, for most of the ones that are out there, it's called mitochondrial disorders. They might add a gene to it, but it's kind of this generic mix-max of everything through your body.
Which makes it really hard to diagnose. Yeah.
Yeah. It's not an easy one. I think it makes it more fun because it's a puzzle, but I understand not everyone has that attachment to it like I do.
That's definitely a genetic counseling approach to that. Oh, it's a puzzle. It's something to figure out. And what I find so fascinating about it is that mitochondria have their own DNA separate from the nuclear DNA. So when we refer to like human genetics, like most people are referring to the human genome in our nucleus. But I think it's the coolest fun fact about it. I mean, maybe I'll learn a better fun fact that, you know, surprises me in this interview. But how does this impact the inheritance pattern of mitochondrial conditions, knowing that it's inherited differently?
Yeah, so again, there's not a simple answer, which is a summary of everything involving the mitochondria.
And genetics.
Yes, very true. When it comes to, like you said, high school biology genetics class, you have the chromosomes that you get half from one parent, half from the other, nuclear DNA. In the mitochondria itself, we actually have little loops of DNA, and it's not like one per mitochondria. It's like somewhere between 5 and 15 different loops inside every mitochondria. Each cell then has lots of mitochondria. It kind of compounds and how difficult it is. Now, when we talk about mitochondrial DNA inheritance, typically we think of that as getting it from the egg cell. Because in the egg cell, back at the stage of conception, there's actually little mitochondria in the egg, and inside of those are the mitochondrial DNA. And so we get it directly from that egg. The sperm have them too, but they leave it behind on the tail, and so, again, usually don't pass any down to the baby. But, fun fact, we've had our mitochondria in the human body since way before we were humans. We've very well integrated with them. So our nuclear DNA and our mitochondrial DNA both tell our body how to make the mitochondria and how to keep it functioning. So about 20% of people with mito, again, general numbers, will have a mitochondrial DNA mutation, so inherited from maternally or from the egg cell. But the other 80%, it's actually either inherited from one or both parents through your nuclear DNA. So again, leads to more confusion even with doctors, because they're like, I remember the mitochondrial loops. And I'm like, that doesn't apply to 80% of people.
That's a big number. I would have thought it would have been the opposite, that most mitochondrial disorders are inherited through the mitochondrial DNA. Wow, that's surprising.
Think about it this way. There's 37 mitochondrial genes, 20,000 nuclear.
Yeah, that's a good point.
And what did we find first? All the mitochondrial ones. So it used to say that in the textbooks, but it's newer papers, that percentage is dropping as we find less typical cases, people who present later. With a lot of genetics, we find the cookie cutter answers first, and then we open it up to everything else.
Right, that makes a lot of sense. And oftentimes when I think about like a typical cell drawing, like a diagram in a textbook, they have two mitochondria, and it's like those two in there. And it wasn't until, I don't even know when, if it was grad school or undergrad for me, when I found out that is not true at all. How many mitochondria are in a cell, and like how does that affect, like some of your mitochondria could be affected and some don't? Can you expand upon this?
Yeah, so essentially that diagram is beautiful but wrong, right? So we really have more like 100,000.
So that didn't fit in the picture. It didn't fit in the textbook.
No, I mean, you had to do a lot of dots. It would just become a giant black shape, right? And then inside each mitochondria, right, there's that 5 to 15 loops. So I just tend to be like, we've got millions of this stuff, because trying to calculate it's not helpful at that point. Why they're all so hard is it's not like we can count them. So I have little mitochondria stuffed animals I always keep around, right? You can't be like, well, I have 1 in this cell. Wait, no, I have 2. Wait, no, I have 3.
Y'all got to get on YouTube if you're listening to the audio version of this, because it's amazing.
Yeah. So it's not that these exist separately from each other. It's more like droplets of water on a window. They're constantly merging and redividing. So even when you're like, I count them, it gets really complicated fast because they're not static. So it's not an easy yes or no count, which is part of why it's harder to try to figure out like what percentage of your mitochondria aren't working. Well, your body's constantly trying to remove the not working ones and fix things and alter it. It's a dynamic picture. There's cool videos of that on YouTube too. You can actually see the lights like combined and separate again. But when it comes to like diagnosing a person, so not fun science, but practical, right? You can do tests where you look at mitochondrial DNA. So they actually take out those little loops, sequence it, so run spell check on the DNA and say, hey, do we see the typical, what we expect 37 genes to look like? Do we see any spelling variants in them? They typically will give you a percentage on that. They'll be like, so out of your muscle biopsy, blood, saliva sample, you might say that you have 90% heteroplasmy. So 90% of the DNA we looked at carry that same spelling change, but 10% didn't. Again, rule of thumb there is like, well, if it's only in 2%, maybe that's not causing you symptoms. Maybe that's normal variation. If it's in 90%, a lot of them aren't working. Maybe that's what's leading to this patient's symptoms, with the understanding that you can have different percentages depending on what day you test or what organ you check, right? It's not consistent through your body because constantly moving and changing. But then again, there's always those exceptions to the rule. A lot of people are like, a higher percentage equals you're more likely to have more severe symptoms. But then you look at LHON, and again, typically, though not all the time, 100% of that mitochondrial DNA carries the same change. So it's not that your heart might be more affected because it has more mitochondria that aren't working. It's your whole body, every cell has that same change. Also, that means all of your eggs do. So if you're having children and you have egg cells, all of your children then will have that change in every cell in their body for generations in either direction. But not 100% of people with LHON demonstrate symptoms. So it kind of matches and doesn't match sometimes what doctors know about mitochondrial DNA. And that's why I say it's not a cookie cutter answer pretty much ever when it comes to the mitochondria.
Are you seeking a position as a genetic assistant? People in these vital roles aid with clinical and research patient communication, data entry, genetic testing coordination, and administrative tasks. Therefore, training is key. We recommend the Genetic Assistant Online Training Program at Johns Hopkins University School of Medicine. This online program provides knowledge and skills to learners considering genetic assistant positions or those recently hired into these roles who need job training. This program consists of 2 10-week instructor-led courses. All you need is a basic understanding of science, particularly biology. At the successful completion of the program, learners will receive a certificate of completion from the Johns Hopkins School of Medicine and the McKusick-Nathans Department of Genetic Medicine. Applications are closing for the fall cohort, which starts September 12th. A limited number of partial tuition waivers are now available to help offset the costs of the program. Don't wait. Check out the Genetic Assistant Online Training Program at Johns Hopkins University School of Medicine now. Click the link in the show notes for this episode for more information. You can also access that link via the blog post for this episode available at dnatoday.com. PerkinElmer Genomics is a global leader in genetic testing, focusing on rare diseases, inherited disorders, newborn screening, and hereditary cancer. Testing services support the full continuum of care from preconception and prenatal to neonatal, pediatric, and adult. Testing options include sequencing for targeted genes, multiple genes, the whole exome or genome, and copy number variations. Using a simple saliva or blood sample, PerkinElmer Genomics answers complex genetic questions that can proactively inform patient care and end the diagnostic odyssey for families. Learn more at PerkinElmerGenomics.com. Yeah, so Lissa, I would love to pull you into the conversation because your son Jeremy has LHON, and can you tell us a little bit about him and what his first symptoms were that you identified?
Yeah, absolutely. So Jeremy is really kind of a prototypical LHON patient. It's just a very typical LH1 presentation because back in October 2008, Jeremy was just turning 19. He was a sophomore in college and he was walking around on campus and there was a billboard that he walked by every day. And one day he went, that looks blurry. Didn't look blurry before. So, typical college kid calls mom and says, hey mom, I think I need contacts or glasses. Can you set me up with the optometrist? And that was really how it all started for him.
So is that a typical age to start having symptoms? You said, he was like a sophomore, so like 19 in college. How does he compare to other people in the community that have LHON?
People can often refer to LHON as a young man's disease. Even though really about 25% of the people who are affected are female, people look at the 75% that are male, and that's what they think of. And then within the males, onset for about half of them is between ages 14 and 26, with kind of a midpoint of 1920. So again, he was very typical, teens, early 20s for a male. That's where half of them occur. But then there's the other half that are younger and older, and there's the 25% that are female. But that's where Jeremy fell on it.
Interesting. And so for Jeremy, how did things progress from there? Did blindness increase over time? What has his experience been?
So what happened was, between the time he called me in late October and I set him up with an appointment when he was going to be home in November, didn't sound like a rush. By the time he got in the optometrist chair the day before Thanksgiving, he covered one eye and his vision was 20/30, just slightly different from his year before visit at 20/20. But then he covered the other eye, and the doctor was asking him to read the letters, and he kept telling the doctor, well, put the letters up. And the doctor kept asking, upping the size. Jeremy didn't know it. And he kept telling him to read, and he couldn't see anything. And finally, he had the big E up, and Jeremy was still telling him to put the letters up. And when he took his hand down and just saw that the big E was up there, because his one eye was functioning, the other wasn't, it was like, ooh, something's really wrong here.
Yeah, that must have been very scary in the moment for him, and also for you as his parent, to just process that at such a young age. Did you have any family history of this, or was it more of a sudden finding for your family?
It was a sudden finding for our family. Of course, I started scrambling to find out what it could be. And when I started reading about potential genetic causes, particularly on the maternal bloodline, I started trying to, my mother was an only child, so I didn't have a lot of relatives to contact, but I did find one living relative. And when I said to him, did you ever hear any stories around the dining room table, about someone going blind suddenly? And he said, you mean like my dad? I was like, bingo, this must be what it is. And so that's, I think, how a lot of families learn about it is they don't know about family history. And then it happens, and then they find out. But that's when I thought it must be LHON, and that's when I talked to the neurologist. But the neurologist, while we were going on that exploration, it wasn't automatically what it was. The first thing was, is it a brain tumor? So we were in the ER on Thanksgiving, and it wasn't a brain tumor. That's great. So then they thought it was optic neuritis, because that's usually what causes sudden onset vision loss in one eye. So he had IV steroids for several days and was told it'll get better, but it didn't. And then the kicker was, while he was getting that treatment in December, the second eye started to fail, because that's the hallmark of LHON. About 6 or 8 weeks after the first eye failing, the second eye starts to go. And when you just have one eye not seeing properly, your other eye compensates, and you're thinking it'll get better and life will be fine. But all of a sudden, that second eye starts to go, and it just gets worse and worse and worse, and there's nothing available to compensate. And that's when it gets really panicky and scary. And his neurologist thought he had neuromyelitis optica, so he did plasmapheresis for a couple of weeks. But it was the wrong treatment for the wrong diagnosis. But it takes time to get the genetic test result for LHON. So, that's what happened. Finally, we found out what it was.
And do you remember about how long it took to get the genetic testing back, once Jeremy submitted a sample?
About 3 weeks. Felt like a lifetime.
Which is a long time to wait. That's a very long time. Yeah, I can certainly, relate I'm in the prenatal setting, and when testing takes that long, it feels like a very long time for patients when they're sharing that.
And getting into a neuro-ophthalmologist was, I think, the hardest part, was getting the appointment. Because optometrist, ophthalmologist, neurologist, neuro-ophthalmologist, all I knew about was optometrists. I didn't even know all those other things existed, or what they did, or why. So working my way through that system was, I learned a lot, but it was complicated. So getting to the right person, and then genetic counselor, didn't know you guys existed until the neuro-ophthalmologist had him work with a genetic counselor. But that was, again, it was all new.
Yeah, certainly. And I think for people to understand, it's helpful to know how this works on a cellular level. So we've talked about how this is a genetic change that leads to these symptoms, but we haven't really talked about the middle part of that, of how the mutation leads to blindness. Does one of you want to explain how that works on the cellular level?
The way I would explain it is that there's 1.2 million optic nerve fibers that connect from the eye to the brain. And so it's those retinal ganglion cells that are preferentially affected when LHON onset begins. So those nerve fibers start to swell, which causes the blurriness. And of those 1.2 million optic nerve fibers, some are small, some are medium sized, some are large. And the small ones are preferentially affected, which means those are the ones controlling your central vision, which is what you need to focus on small detail. So the first thing that happens is, your central vision is gone. So you can't read without magnification. You can't recognize faces. Everything that's in front of your eyes is just a scotoma. It's a blur. And the scotoma starts really small, but then it gets bigger and bigger and bigger. And what's left is your peripheral vision. And with some people, like with Jeremy, he's really fortunate. He has a good amount of peripheral vision, so he can navigate his environment. He doesn't bump into tables. He's got, especially once he adjusted, he does very well with his remaining peripheral vision, and he magnifies things and can see things, although some things have to be auditory. But for some people, they don't have as much peripheral vision, and that makes navigating life more difficult. But really, for everyone who is affected by LHON, almost everyone, of course, as Devin said earlier, there's always exceptions. There are certain mutations that tend to have a better outcome. When people are affected in childhood, they tend to have a better outcome. So there are exceptions. But generally speaking, most people will become legally blind. They will have a central scotoma of some certain size. They won't be able to drive. They won't see faces, much less recognize who people are. They won't be able to read without magnification. Yeah, that's what happens.
And we mentioned earlier that some people can have mutations but not have symptoms for mitochondrial disorders. Is that the case for this disorder, where you can have the pathogenic variant, the mutation, but not have symptoms from it? So can people be asymptomatic?
Most people who carry an LHON mutation will live their lives and they'll never have a symptom. They'll never know they had it. Or they may have a family member that is affected, but they never will. And the percentages are under discussion, and people are learning all the time. Like Devin said, there are certain things that you find in the literature everywhere that people believe strongly to be true. For instance, it says pretty much everywhere that if you're a male and you carry an LH1 mutation, it says you have a 50% chance of losing vision in your lifetime, but that's really not accurate. Based on knowing hundreds, if not thousands of people globally, having gotten to know a lot of folks in the community, that's simply not true. As backed up by a fairly recent paper by a team in Australia that has studied deeply. That's based on very old information from the pre-molecular era, before there was genetic testing, and you had to have it in your family before you could call it LHON. So the real...
Right, that's going to sway it a lot.
So maybe it's more like 20% of males who have it. But even that may be wrong. So no, most people who carry it, it does not mean they will have that symptom, no.
Which is so interesting to understand, and I'm sure a lot of it we don't understand yet, of what makes that person symptomatic or asymptomatic, of knowing those other factors that are involved. I mean, do we understand why it affects males more than females?
So the current thought process on that is it's believed that perhaps estrogen is playing a protective role. Perhaps estrogen is prompting additional mitochondrial biogenesis. So maybe we're making up in quantity what we lack in quality, and maybe that's protecting us. And is it possible. As I think I mentioned earlier, the median age of onset for males is 20. Women, it's a much more even onset throughout our lifetime with a median around 30. So is it that estrogen is protecting those of us who carry an LHON mutation, and perhaps more of us when estrogen drops later in life? Is that causing more onset? It's a theory. It's being investigated, but it's not fully known yet.
Interesting. Yeah, a lot more research I feel like that we need, and that has been done recently as well. As you were saying, like some of these papers are so outdated, you really have to look at dates, especially in genetics. They're so important. So I'm curious, are there any clinical trials that are underway? Is there anything that is currently being developed that can possibly be a helpful treatment for people that are symptomatic?
I think that in terms of, you asked if there's any current clinical trials, and unfortunately the answer is right this minute, no. In the time that I've been involved since 2008, yes, there have actually been quite a number of clinical trials. We've actually been very fortunate as a rare disease to have quite a number of trials. And there have been studies of antioxidant approaches. There have been tetrapeptide studies. There have been gene therapy trials. So there's been a lot of investigation that's gone on. And one really good thing is as a rare disease population, we're a generally healthy group of people. We just don't see very well sometimes. But we're highly, as a community, we're highly motivated to participate in clinical trials and generally capable to travel as needed. So we've been able to quickly populate trials, and I think trial sponsors really appreciate the fact that we've been able to accomplish that. So that's the good news. There is one approach, an antioxidant approach, that's been approved by the EMA. So in Europe, it's an option, but it has not been presented here in the U.S. as an option for a lot of reasons. And then, like I said, there's been a lot of work in gene therapy, and there are plans to present that to various review bodies, but it has been presented to the EMA, not yet to the FDA. So it has, we haven't yet had the outcome that we're looking for, which is, an absolute treatment cure. We've had approaches, and hopefully there will be more. There's also the interesting option of mitochondrial replacement therapy, which is being explored in the UK at one particular center, and Australia just approved it to be looked for further into, and the ethical board in the US that reviewed it had approved it, but then there were rulings made that it's not allowed here. So that's another approach that's being explored.
So much to keep track of. Wow, that's really good that there's things on the horizon. Devin, go ahead.
I was going to say, and one thing I want to throw out is there's always the flip side of treatment, which is also prevention. And LHON is a condition where there's a lot of knowledge about what can you do to try to prevent that onset, which in the genetics world, to me, feels amazing, because a lot of genetic syndromes, we don't really have that discussion to have. It's, well, you have it, good luck, right? And that's kind of the reality for a lot of conditions. So I wanted to also give her a chance to talk about, what are some of those really common things we know, because they actually do make a huge impact.
Yeah, thanks, Devin. No, I think it's an important topic that it's complicated and interesting because on the one hand, it's wonderful to know that there are things one can do to reduce one's risk. It's also complicated because, as you would know more than others, having difficult conversations in the family. Imagine that you have a 19-year-old son who loses vision, and so you have a 16-year-old and a 13-year-old, were the ages of my other children, when Jeremy lost vision. And I learned that being around smoke quadruples their risk, and mine, obviously, because I'm an obligate carrier also. So, for all of us, being around smoke is a risk factor and kind of quadruples our risk of onset. Alcohol, consuming more than a glass a day, is strongly believed by some, although it's not fully agreed upon, as a potential, way to reduce risk. So some people receive that information and say, wow, those are things I'm going to avoid. Other people say, you're ruining my lifestyle. I don't want to think about that. I want to just live my life. So we have really interesting conversations in the community and within families about how to deal with that information. But the information is there. And again, it's not like anyone's done a clinical trial where you put 100 people in a box and exposed them to smoke and 100 people you didn't. So people always say, well, it's not proven. Okay, it's not proven, but there's other ways of suggesting, and people make different decisions based on the information, and we're learning more and more all the time.
And I also wonder with this, like something that, we talk about a lot in genetics is looking at IVF and different procedures that some of this, for other types of disorders, like more autosomal recessive disorders, a couple may do IVF and choose an embryo that won't inherit a certain rare condition or condition. But there's also talk of using like a donor egg and then taking both of the intended parents' nuclear genetic information and then inserting that into the egg so that you're not inheriting the mitochondria from a parent. Is that something that is talked about in your community? I mean, I don't even know if we're doing this yet in the US or anywhere in the world.
That's what I was mentioning earlier. That's the MRT, the mitochondrial replacement therapy approach. That is being done in Newcastle, in the UK. That's the one location where it is actually taking place. And then Australia has something called Maeve's Law, and they just passed that a couple of months ago. And so
Okay, I missed that was the procedure.
I said it real fast.
Okay.
So, yes, that was it.
Well, and to be honest, when it was on the news, it was mostly articles that had the unhelpful name of 3 parent babies. And
I was like, do I even say that? I'm like, I don't know. Yeah.
It's how a lot of people have heard of it. So I think it's sometimes helpful to mention while mentioning that it is a horribly come up with name. Yeah. In my opinion.
I think it's more like almost like donating an organ. I feel like that's more close to what it is, that's the way Laura Hersher explained it to me. And she's been on this podcast before. And I felt like that was closer to what it feels like than having 3 biological parents. It's like, yes, technically. But
I heard someone describe it as a 2.001 parent baby, because the contribution of the third person.
We got to rewrite that headline.
It's that minuscule of an impact that the third person has on the process.
Yeah. 37 genes, 20,000 genes.
Yes. If you're getting 10,000 from each parent, and it's like whatever. But yeah, that's just kind of, I think good for people to be aware of that's what those headlines meant. And kind of deconstructing that. But before we run out of time, Devin, I would love to hear a little bit more about your experience with having a nano-rare mitochondrial disorder. And you got to tell us about the mouse model, because I heard about this and I definitely geeked out about it.
Yeah, so luckily I find all of this really fascinating, or else maybe I'd be more annoyed with my life story. But the short version is, I had failure to thrive as a baby. I went home, got better. We kind of ignored it, thought it was a fluke because I was just a very tiny, tiny baby. And then when I became a teenager, I started getting sick a lot, missing a lot of school. They thought I had mono. My brother, though, presented with more severe muscular symptoms and liver involvement, and so he was the guinea pig. I forever owe him a debt for this. He got a bunch of biopsies. He had a bunch of tests done. They diagnosed him with mitochondrial DNA depletion syndrome. So look at the mitochondria, look at the little loops of DNA. There's not as many in there as you would expect. And then they looked at me and went, oh, this explains a lot. I was missing 80 out of 180 days of school. I didn't understand why I was sleeping 12 hours a day. The hindsight's 50-50, right, in that case. Now, I never saw a GC in the process, never saw a genetic counselor. They did a bunch of genetic testing through clinical labs. Nothing popped up for my family. So again, I have a lot of privilege that my muscle biopsy was abnormal. So I had a diagnosis, even though genetic technology hadn't caught up to us yet. And it was through a research exome at the University of Washington Medical Center, a software update, and some absurdly smart individuals that all came together, and they found that a gene, GUK1, that tells your body how to make one of the 4 letters that writes the mitochondrial DNA, that set of instructions wasn't working the way it should.
That sounds important.
So when That's the logic, right? If you're trying to write a book and you're missing a fourth of the letters, it's going to be really hard to read that book. Those instructions are going to be really hard to use. Your body has trouble making the proteins. My poor little mitochondria on the report say they're markedly mutated. They didn't look so great under a microscope. I still want a picture that they never gave me.
Yeah, that would be cool to have.
So annoyed. I was like, I want to see what do we mean?
Right, like I have a picture of my karyotype. Like I have it up on my wall. Like, yeah.
Mine was my Facebook profile picture when I did it in undergrad.
Yep.
Like how you know you're a genetic
Totally.
So what, again, I had privilege of, we already had been connected with the world leading expert on mitochondrial DNA depletion before we even knew we had that. Dr. Hirano in New York City. He took my skin biopsy, looked at my little mitochondria, counted how many of that letter I had, said, oh, you have 20% of what you should. That means that genetic mutation, that probably is your answer. That's what they call functional studies. We have proof that the theory is happening in the cells. And from there, we made a little mouse model, tried to make them look like me. I really wanted a pet mouse that was me. Didn't work. Mice were too affected to be born, so now we have little mices that look like my dad and my mom and two of my parents' mutations in one. And essentially now we can test treatments. And what I think is so cool about that is literally the treatment is taking the letter that you're missing for your DNA and putting it in pill form and taking it.
That sounds simple enough.
And right, yeah, it sounds super easy.
Like, come on, why do we not have that already? Like,
well, we do.
We do.
That's the fun thing. It's just for a different letter.
So we're close.
We're following someone else's blueprint,
all right,
which is a very, very helpful. Again, very privileged that a blueprint existed that my family could follow.
Right, a lot of dominoes fell into perfect place for you to even have a diagnosis.
Oh my gosh, yes. And I mean, on average, mitochondrial disease at clinical diagnosis, only 40% of people with it find a genetic answer for their symptoms. It's similar to things like epilepsy, autism. They all have about that 30 to 40% rate. But that means 60% of people are running around and people are like, are you sure you have that? Because we haven't found your mutation yet. Maybe you're making this up. Maybe it's not this. It's a hard place to be. And I'm incredibly lucky that I'm not still in that place. But it's part of why I'm very patient focused for my patients. Because I'm like, look, I found answers through a lot of privilege. 99% of people can't get this answer or this potential hope of a treatment, which is just mind-blowing to me. It's still taking like a decade to make it, but that's science, right? You have to make sure your body doesn't destroy it when you take it via pill form. You have to make sure it gets to the mitochondria. It's a process. You have to get supplies from China during a COVID outbreak when you can't get any supplies from China. Like, there's a lot of steps involved, but to me, it really affected, like, how do I approach my patients, right? A genetic answer that gives you hope, that gives you progress, that gives you clinical trials to look into. It gives you a community. I always believe my patients. Sure, maybe someone lies. We all do. Or maybe someone's not describing their symptoms perfectly. That's not my point. Like, symptoms, believe your patient when they're saying they're going through that. Figure out how to help them and get them connected with good support organizations. Like, for me, Mito is a community. It's now my obsession on Etsy, right? This is a custom-made one because I messaged the shop owner and was like, can you please make me a rainbow one?
I love it.
Like, it's become a huge part of my life. Just a little shout out. It's for fresh crayons.
Yes, we'll put a link in the show notes to kind of send people
right?
in that direction. And you've run a support group for teens with mito conditions, right?
Yeah, so when COVID started, we started doing Zoom calls. And we do them every Friday night for 2 hours for teens and 20s with mitochondrial disease. That is expanding on a Facebook group we started about a decade ago because we met at a conference and selfishly didn't want to lose touch with each other. Started a Facebook group. Now it has like 500 people in it. And now we meet weekly and we have prom and people have their kids named after each other and have been to each other's weddings. Like, it's a community. It's not a diagnosis. And it's part of why I'm so dying on the hill of I want people to get access to genetic testing and to community supports and someone who explains the value of that, because it's completely changed my life. I'm wearing a DNA mito necklace I didn't even realize.
That's amazing.
Right? Like, it's a huge part of
my
life.
It is, yeah.
It's a positive though for me, and yes, there's hard parts of it for sure, but it's not only the hard parts.
It seems like it's also part
an
of
important
an
detail.
identity as well, if I'm getting that right. I don't want to overstep, but yeah.
No, exactly. No, I fully admit I identify as disabled because of this. It's part of who I am, and I think it's part of what makes me a good provider.
Yeah.
And makes me connect to my patients more and put in the extra hours and do the due diligence and answer the emails from Google at 3 a.m. that people found online. Because I know that that's actually really important to have someone to answer that 3 a.m. question.
It really is. And I just want to thank you both for being such amazing patient advocates and also being so open about your families and your experience. And, you know, I think I really appreciate that. And I think the listeners can tell when people are just so passionate about this and just so open. I think it goes a long way. I think this has been an amazing episode, and I just want to thank you both so much for taking, you know, the time and energy to come on and just share your expertise in your lives.
Yep. And I will send you links for some of the main organizations and for Lissa's website, because she also does Zoom calls for all different people. So I'll send you that too.
Awesome.
So if people find it, they can.
Yeah, you guys can go to dnatoday.com and then click on the link for this episode. And then you can find all the links there that Devin's going to send me. So thank you guys so much. I really appreciate it. Did you know PerkinElmer Genomics was one of the first laboratories to offer whole genome sequencing on a clinical basis? Whole genome sequencing can maximize clinical diagnostic yield for patients. With turnaround time of 4 weeks for the proband sample, PerkinElmer's whole genome sequencing test is designed to provide access to additional valuable information compared to an exome. PerkinElmer also offers prenatal whole genome sequencing as well as ultra-rapid whole genome sequencing for critically ill newborns using dried blood spots. The ultra-rapid genome has a turnaround time of 5 days and includes mito, chromosomal CNV analysis, STR-TNR screening, and biochemical analysis. Also, listen back to episode 176 with Dr. Madhuri Hegde, where we explored the power of whole genome sequencing, which also happens to be one of my favorite episodes of DNA Today. And stay tuned for a couple more episodes with PerkinElmer soon. Discover all that PerkinElmer Genomics has to offer at PerkinElmerGenomics.com. Are you interested in the rapidly growing field of genetics and want to learn more about clinical genetics, molecular genetics, and laboratory science? Then you should check out the Genetic Assistant online training program at Johns Hopkins University School of Medicine. By taking part in the program, you will be joining both national and international learners with the same passion for genetics. Interact directly with your Johns Hopkins instructors and fellow learners throughout the program. Applications are open now for the fall cohort, which starts on September 12th. For more information, you can use the link in our show notes if you're listening to this through a podcast app. You can also access the link at dnatoday.com. For more information about today's episode, visit dnapodcast.com, where you can also stream all episodes of the show. We encourage your questions, comments, guest pitches, and ideas. Send them all into info@dnapodcast.com. Search DNA Today on Twitter, Instagram, YouTube, Facebook, so you can connect with us there. And a favor, please rate and review the podcast on Apple, Spotify, or wherever you listen. This truly helps us climb the charts and allow more genetic nerds like yourself to find the show. DNA Today is hosted and produced by myself, Keir Deneen. Our social media lead is Corinne Merlino. Our video lead is Amanda Andrioli. Thanks for listening, and join us next time to discover new advances in the world of genetics.
The genes of you and me, the genes of you and me, they're all made of DNA. We're all made of the same chemical DNA.